Hi to everyone. Today I will speak about how to detect periodic pattern in time series, and in the introduction I will speak why we are doing this. So basically I will introduce what is anodot, what we are doing, and what is anomaly detection, and why do we need to modelize time series, and especially this is the purpose of my my presentation. Why, in this context, why periodic pattern modeling is so important, and then I will present basic strategies of how to in fact detect a seasonal pattern, and I will explain how to transform those standard methods to allow to run for millions of time series, and especially to allow us to allow the algorithm to run for big data. So, just a few words about anodot. So basically what we are doing, we are receiving lots of data from our clients. What is the data we call in our world, we call metrics. This is mainly time series. This is values indexed by time. So we receive lots of metrics. For instance, for customer, it's more or less 1 million metrics by customer. So it's huge. And what we are doing, we are processing, we are learning the model of the time series, what is normal, what is abnormal. And then we have tools to visualize the time series. And we have the possibility to create alert. This is exactly the purpose of what we need modeling time series. And then the platform has the possibility to understand what happened in the system. So first, what kind of metric do we receive? In fact, we are receiving lots of different type of time series. This is an example of a series that monitor web service, for example. And in blue we can see the normal state, and in orange this is the abnormal state. I will explain what is abnormal state after. Another example, this is time series came from IoT. This is the time series of temperature in a factory. So in some industrial process, the temperature needs to be very controlled. So this is another example of what kind of time series we have. We also have some problem in security. For instance, this is the case of fraud detection here. And we also have business. Business metrics are really interesting because, in fact, most of the time they are mainly the same pattern. What I mean by this, we can see you have more or less 5 daily patterns, and during the week this is lower. And in fact, this is more or less the general pattern that when humans are interacting with the system, and this system is monitored. So in this case, this is for instance HTTP request on a web server, on public web server. So this is all the variability of time series that we have, that we receive. What we need now is to find anomalies in this case. So there are people that are talking of us. So since last week we are Gartner cool vendor of this year. So this is very cool. And also the press are talking of us as an Israeli startup in Bay Area. So it's also cool. But also we have lots of customers that we are really proud to work with. So we have Wix in Israel. I think lots of people know what is Wix. And we have also signed in US with Credit Karma, which is a very big company. And of course we have lots of other clients, but I don't have the place for all of them. So now I will explain how to create an anomaly in anodot. All the task is completely in real time. So this is very important to have a potential value, operational value. In fact, this system, you don't have to wait until to receive the alert. This is very important because since you need to take operational action, you need to be real time. So this is the general pattern is we receive a time series. First, we have a model. We have an online model of the time series. So we understand the normal behavior of the time series. What I mean by this, first we model the trend. So for instance, in this case, this is mainly stable. Okay, the average is globally stable. Then we have the season, which is the periodic pattern. Clearly, in this case, we have a periodic pattern, which means that there is something that it is the same across the time. Okay. We also have the noise, and sometimes we also have anomalies. In fact, standard time series can be very complex. So, since we have the normal model of the time series, we can, in real time, classify if the state is normal or abnormal. If the state is abnormal, we are also grouping with other metric. In this example, we have only one metric. But think that in real organization, when you have a problem, for instance, on the server or something else, it's very, very, very rare that you have only one metric. In fact, you have most of the time 1,100 metric at the same time. And we have another algorithm that is not the purpose of the speech here, how to link the anomaly across the time for the same client to produce which calls a real anomaly, and then send to the client, okay, we have a problem. After it creates an alert. So I will focus my speech on the periodic pattern detection. Why is so important? So here we have an example, which is a standard example of what kind of matching that we can have. In this example, we can see in blue we have the real data. In the gray band, this is the normal range of our model. In this case, we can see that the model, we don't integrate the concept of seasonality. There is no periodic assumption in this model. So it's very bad for us. It's very bad because, in fact, the band is very, very wide. So we can miss lots of problems. Let's try to assume that we have now a periodic pattern and a daily periodic pattern. In fact, it starts to be better. It's better, in fact, since it's closer to the real data. But in fact, as we can see, we choose to have only the daily pattern. But obviously, in fact, it's a weekly pattern, since we have 5 pikes and 2 lower pikes. So clearly, the best model here for human is the weekly pattern. In fact, the model is better, but we can improve. Let's try with a better model. So we can see if we are able to find the correct periodic pattern for this metric, the model will be very perfect. This is the purpose of, this is the idea of how to detecting of this is the goal of detecting the periodic pattern. And in this case, we can see that we can, every point that is outside the gray area would be flagged as an anomaly. So it's very, very sensitive. Now the model is very good for us. So I will explain why it's so important to detect the periodic pattern. So I will show you some, let's say, difficult example of periodic pattern that we have. The first one here, this is a mixture. We say in amplitude modulation. In fact, this is a multiplicative model of 2 different periodic patterns. We have clearly a daily pattern. Every peak you are seeing is a daily pattern. And we can see that there are 5, let's say, higher peaks and 2 lower peaks. And in fact, this is clearly a model for a week. And as I explained before, this is really common for all metrics that are linked to human activities. Another example, this is what you can see here. This is the additive signal. We have the daily pattern. And we also have an additional periodic pattern. In this case, this is 3 hours or 4 hours, I don't remember. And most of the time, this is because on the same machine you have two different processes. For instance, typically this is a process of a web server, and we added a periodic cron job here. And what we want is to be able to detect the small anomalies in orange. Okay, and I also added the zoom because you can see, for instance, there is some example of anomalies in the time series that we want to catch that are very hard to catch. So now I explain why you need detecting the periodic. So the goal now we'll try to construct an algorithm that just produce, okay, this metric has a daily pattern, this metric has a weekly pattern, or something else. This is the only purpose of the algorithm that we need to create. In fact, in the literature, there is lots of possibilities, but mainly we have two classes. The class based on, let's say, the Fourier transform. I will explain what is it after. And the second class is all the algorithms that are based on autocorrelation function. So I will explain both of the two algorithms. So the Fourier transform, I don't remember if at university, maybe it's very old for some of you. This is mainly to decompose the time series in their component of sinus. So the algorithm is more or less complex, but this is the idea. And you can see the example. We have two sinusoidal functions. In the time domain, this is just an addition. So you can see that in time domain, this is more or less complex. In frequency domain, which is in the right, we clearly see two different spikes. So clearly, this is what you need. This is exactly what we need here. So from this algorithm, we can derive an algorithm. First, we will compute the Fourier transform, which is called the spectrum of the time series. Then, let's find the local maximum of the spectrum. And after, you need an algorithm to be more or less robust with all kinds of phenomena that can occur. So we need, let's say, an heuristic to decide which peak is good. So this strategy seems to be promising. So let's pick an example. This is an artificial example, which is a sinus, which is a little bit noisy. And clearly the spectrum, we clearly see a spike, which is clearly located at the place where I expected. This is the one-day spike. So for the moment, everything seems good. But let's try to see some examples that can occur in the real life. First, this is the problem which is called the harmonic problem. In fact, all the Fourier transform is based on the idea that it's composed of sinus. But most of the time, we never saw sinus in the real life. And for instance, I took an example from some spike, which is close to the reality because, in fact, most of IT-linked metrics are with spikes. In fact, for instance, things on a server, you can have a cron job that cause a spike on CPU load, for instance. Okay, and we can see on the right the spectrum now. So first, there is not only one peak. There is lots of peaks. So we said in the theory of Fourier transform, you say that in fact all of the first peak, this is the fundamental, and other peak are the harmonics. And the question now is, we need only the harmonic. We need only the fundamental frequency. This is the only things we need for the algorithm. So the question, if we are choosing an algorithm that picks the local maximum, in fact we can catch an harmonic, which is very problematic because in fact you can have a metric that is daily, and we can say that in fact the period is the harmonic, so we can say 12 hours or lower. So this is problematic for the modeling. In fact, if we catch the harmonic, we'll have lots of problems. So, in fact, we say in this case that the energy of the series is spread across the harmonic. So it's hard to identify the correct frequency. Now this is a zoom. This is the zoom of the first 5 harmonics. And in the blue, what you see is the first line. This is the correct frequency of the metric. And after, this is all the multiple of the frequency, which means that the first line, this is the let's say, let's say 1 day. After, this is half of a day, quarter of the day, and so on. So okay, this is one problem that can occur with Fourier transform. I will show you another one. In fact, most of the Fourier transform is linear. For most application, it's a good advantage. But in fact, in this precise case, it's a big disadvantage. Why? Because things, for instance, if you have a time series that have a periodic pattern, which is S, which have noise, which is N here, and also anomaly, because in our case, we assume that we have anomalies. In fact, since it's linear, the noise and the anomaly will contaminate the spectrum, which is another problem for identifying the correct maximum. So let's try an example to better understand. So this is the same example, but I just change the level of noise. So in this example, for the first example, first you can see that the first peak is not clearly defined. If you choose only the maximum peak, we don't catch the first one, which is, first, this is the problem. But let's assume we have a workaround to identify, but let's increase the noise now. If we increase the noise, okay, now this is the first one completely disappear, the maximum is the second one, so in this case the algorithm will return half a day instead of a day, so which is clearly a mistake. And if we increase again the noise, now the first peak completely disappear, second one, third one, and in fact the maximum is the third one. So in fact we can see that in presence of noise relatively reasonable, because in fact human can understand that clearly there is a periodic pattern here. In fact in the spectrum we can see the periodic pattern. So in fact this is clearly a case that the Fourier transform will fail. Okay, this will fail. Let's try the other class of algorithm that has been already published. The general idea is to use autocorrelation function. What is autocorrelation function? Basically, what we are doing with autocorrelation, this is the formula. This is not really important. The only things to understand is we are shifting the time series, and then we are computing the correlation with the two series. Okay, the formula is the classic formula of correlation. So, what is the mechanic of this algorithm? So, what we see here, we have this is the same time series. We are shifting the time series with the time. So the blue one is the shifted one. And we are computing the correlation between the blue one and the black one. And at each point, it's creating a correlation. Maybe again. Okay. The first thing that we can see here in this example is the autocorrelation function is also periodic. If the original series is periodic, the autocorrelation function is also periodic. And the maximum of the autocorrelation is exactly what we are searching. This is the periodic value. So again, the idea is to compute the autocorrelation function, to extract local maximum, and then to have an heuristic to determine which is the best maximum. So, what are the advantages? What is the behavior of the autocorrelation according to noise? And this starts to be very interesting, because in fact the autocorrelation of noise is always zero. Always zero. So in fact the autocorrelation function is never noisy. Never. So this is a very good advantage. So if you are summarize the advantages and the pro-cons of which kind of algorithm, we can see that first the Fourier transform, in fact, the main algorithm is called the fast Fourier transform, FFT. And fast, which means that the standard algorithm is n log n. So which is more or less enough for big data scale. And autocorrelation, but in the other hand, it's n square. I will explain why. It's n square. So clearly, in this case, Fourier transform is better. Regarding to noise, I already explained that Fourier transform is clearly linear. So we have it could be contaminated by noise. On the other hand, autocorrelation have better behavior according to noise. So in this case, for this criterion, autocorrelation wins. Another problem, this is the harmonic problem. I explained that since both in autocorrelation function and both in spectrum of the Fourier, we have lots of local maximum. So the question is, what can occur if you are making a mistake in identifying the correct local maximum? In the case of Fourier transform, we will extract the half of the period. So this is problematic. We can say that a time series which is daily has a period of 12 hours. This is impossible. But on the other hand, it's clearly possible to modelize a daily time series with a 2 days period. So this is exactly the purpose of the third line. The error we can make in the Fourier transform is to extract the fraction of the correct period. But in the other hand, in the autocorrelation, the error that we can make is to extract the multiple. So this is good. This is still acceptable. So that's why autocorrelation wins here. A more operational criterion is, in fact, in real data is not correctly sampled. For instance, every minute, every hour, something like this. So there is a lot of different complication. We can have missing samples, lots of different complexity like this. And Fourier transform is a very bad behavior regarding to this problem. And in the other hand, autocorrelation is better regarding to this problem. And also, I also added that discrete Fourier transform for anyone that already work with it have lots of numerical pitfalls, lots of different parameter tunings, windowing problem. It's very hard to deal correctly with it. So the intuition regarding to this table is, okay, autocorrelation seems to be promising, but the problem it's very slow. The only problem is it's n squared, so this is very slow. So the idea is, let's try to optimize autocorrelation function to be, let's say, big data enabled, so faster. So this is some optimization that we made in Anodot. So the idea is, first, why the autocorrelation function is so slow. So in fact, there is two loops. As you saw in video, there is two loops. The first loop is we are shifting. We are lagging the time series, and for each lag, we are computing a correlation function. We are computing a correlation coefficient. The correlation coefficient, I remember here the formula is clearly n. And since there is n shift possible, so the algorithm is n squared. Okay. And this complexity, it's almost impossible at big scale. In fact, in our system, we have more of 10 million of metrics. So clearly, an n squared algorithm, it's impossible to run. Clearly. So let's try to optimize this algorithm. In fact, the idea is to think after. Okay, clearly we need to compute the autocorrelation, but what we really need is to find the local maximum. And we need to compute the local maximum. And we also, the idea of the optimization is to compute the error you can make in estimating the local maximum. Let's pick examples. I have an example which this is the autocorrelation function of a metric which is daily, okay, and we see in green the maximum we want to extract. let's try to calculate the error that we can make estimating this position. Clearly, it depends on the sampling of the metric. So, for example, in the 5-minute sampling, the frequency is 1 day. The error is very slow. It's far less than 1%. On the other hand, if we have an example of 5 minutes, the same sampling, but the frequency is 1 hour, so it's far lower, the error is 8%. So what we can see that, in fact, the error we can make in estimating the period is depending of which period there is in the metric. So the idea is to change the computation of the autocorrelation function in order to take account of this and to have, what we need now is to add the constraint to have not a moving error, because for most of cases the error is far too low. In fact, the idea is to add the constraint that what we need for the sampling autocorrelation is the error is constant. And with a little bit of math, we arrive to the conclusion that the error, the sampling autocorrelation is now geometric. I plot here what it means. In the first line, in fact, we are computing for each point, we are computing the correlation coefficient. And so for very high frequency, for very high period, this is very unuseful, in fact, because we are really too precise. So the idea is to change how many tau we are computing the correlation. And with the correct constraint, we arrive to the new sampling pattern. And then, now, we are doing some calculus. The question is how many points we need to calculate the correlation. In fact, there is only log n now, since we added the new constraint. And now, since the correlation is always n, the new algorithm is n log n. So, in fact, we arrive at the same complexity of Fourier transform. So, in fact, we are combining the advantage of two. So, with this algorithm and other, of course, a lot of other complexity that we need in real time, I will show you some real life example that we are working in Yandodot. So, in this example, this is a real example. This is a web server activity. I plot, this is the active session. You can see in the blue line is the real data. The blue area is our model. In our model, we added the correct periodic value. And you can see in orange, this is the alert that we have detected with this model. And you can see here, I added this example, because we can see that clearly, without the modelization of the period, we can catch this anomaly. Clearly, why? Because in fact, without the periodic model, the bound will be the maximum and the minimum of the data. So clearly, in this case, without periodic model, we can catch this anomaly. This is another example, which is very complex. In fact, since our algorithms are, in fact, they are online, they are learning every time. We can see here in this example, in fact, the customer start to send data, and at a certain period of time, because we need data to estimate the period, in a certain period of time, the algorithm finds the correct period. And we can see the evolution of the model. In fact, the model is very wide at the beginning without the seasonal model, and after it clearly catches the correct value. And this example has another complexity because we can see there is a daily pattern and also a 3-hour sub-pattern. And this is one of the most difficult examples because what we need here is to extract the daily pattern and not the 3-hour pattern. So, last slide. this is the last one. I just picked some statistic for the whole platform, which is very interesting also. In fact, we have 11 millions of metric in our platform, and it's growing fastly. And only 15% are periodic. Only 15% are periodic, but most of the time they are very important for the customers. And we can see statistics. 2/3 are more or less daily with daily pattern, and 1/3 with weekly pattern. And all other periodics patterns are mainly related to IT. So it is from 1 hour to half a day period. So the conclusion is the periodic detection is very important for the anomaly detection. And Fourier transform, which is more or less the main method in literature, is good but have lots of pitfalls. And standard algorithm is better but it's very slow. And I explain how to accelerate this algorithm. So thank you for your attention.